I would not have gotten that. I'm not gonna lie.
You try this one, try. See what you get it for.
You just follow on this one.
Okay, so here's number 4, finally. So in order to make sense of this, you need to put it into just a form of like a pair of differential equations. And to do that, you have to multiply out the matrix. So to multiply out this matrix, we have t squared 0, 0, t multiplied by the vector xy. And so that is following the rules of matrix multiplication. That's t squared x plus 0 times y for the x component, and then 0 times x plus ty for the y component. And so now we can write this differential equation as x dot is equal to t squared x, y dot is equal to ty. And you can put that in vector form. It means the exact same thing. Okay, but now we would solve these as two different differential equations. You know, we can think of this as just a system where we have x dot is equal to t squared x, y dot is equal to ty. So the first one of these, crash. It'll come back. Come on, baby. Okay, so this is the same thing as this system. And so let's start with the first equation. So this says dx dt is equal to t squared x. And I can separate variables. So I get dx over x is equal to t squared dt. Integrate both sides. And we have natural log of x. It's really natural log of absolute value, but our boundary conditions here are all positive, so we're just going to do the positive solutions. So natural log of x is equal to t cubed over 3 plus c1. And I can use the boundary conditions before I get it into a nice form. So this first boundary condition, the one that relates to x, says that x is equal to 1 when t is equal to 0. So natural log of 1 is equal to 0 cubed over 3 plus c1. Natural log of 1 is equal to 0. So c1 is 0. And so I can update my best solution so far, which says natural log of x is equal to t cubed over 3 plus 0. And now we just want to get that in a form where x is written as a function of t. So I can take e to the power of both sides in turn. So e to the natural log of x is x. And on the other side, we have e to the power of t cubed over 3. And so that's the solution of our first of those two differential equations. Yep.
like, so like the way I do it was like, I put in the E earlier, and then I just like remember from Calc 4, it's like, it becomes a new, like C2, and then E to the thing, do we have to prove it that way?
Nope. You can go, so you just went the next step before you solve for the boundary condition, that's fine. You get the same thing.
Yeah,
You still got a 0, right?
yeah.
Yeah.
Okay.
Yeah, that's perfectly fine. Okay, so and then you have a second equation. That's the y equation here. And it says, come on now. Ty. Okay, so we have dy dt is equal to ty. I mean, we're going to solve this the same way. So we have dy over y is equal to t dt. Integrate both of those, and we get natural log of y is equal to t squared over 2 plus c2. And now you could go into the function form and then solve for c2, or you could solve for c2 here. The boundary condition here says when t is equal to 1, y is equal to 10. So we have natural log of 10 is equal to 1 squared over 2 plus c2. And so c2 is equal to natural log of 10 minus 1/2. Anybody have a calculator in front of you? I would just put this into a decimal rather than carrying all these values around. You know, a math professor would be furious that I would say that, but mostly we're setting this stuff up, these skills up to input into computer programs, you know, so this is what's going to happen in the computer program anyways, so 1.80? Okay, and so now we're going to go raise each side as a power of e, and so we get 10 on this side. No, I'm not doing that anymore. I'm going to my update. So I'm going back to my last best form of the solution. And so I have natural log of y is equal to t squared over 2 plus 1.8. Now take e to the power of both sides, and we get y is equal to e to the power of t squared over 2 plus 1.8. And this is equal to e to the 1.8, which is just some number, times e to the t squared over 2. What's e to the 1.8? So this is 6.05 e to the power of t squared over 2. Any questions about that? Okay, and then yep.
Wait, when you're at like LNY before you update, if you move it over, like when you have a C2, do you also make the C2 like e to the C2, and then at the end when you plug everything in, would you do?
You do both. You do e to the whole sides.
Okay.
Okay, so that's why. So this one becomes e to the natural log of y, which is y, and then this one you have to have e to the power of everything on that side, and then you're using the exponent rule to say that it's the yeah. Any other questions about that? Yeah.
So when we end up with e to the c, do we simplify that down to just c?
Yeah, you can make it a new C or C3 or whatever. Yep. But you'll get that same answer in the end.
Oh, okay. So if you get a c before you're at like your final form of the function, you just plug
Yeah.
whatever you got before. Oh,
Right. Right. So your new C is, when you solve for it, is going to be 6.05.
Yep. Okay.
While I'm on this, I might as well do number 5. Just talk about that for a sec. So what's different about number 5? So in this case, if you multiply this matrix out, you get, so we're going 0, 2t, negative t, 0, times xy. And for your x component, you get 0 times x plus 2ty. And for your y component, you get negative tx plus 0 times y. So 2ty, and then for the y component, negative tx. And so now we get this form that says x dot is equal to 2ty, y dot is equal to negative tx. And now we have this thing where you have y's in your x's and x's in your y's. And so that is coupled. And so in this class, we have the luxury of saying we don't know how to do that. Really, you can do that, but we're just not talking about how. Any questions about that one? Any other homework questions you'd like to see? Okay, well, let's just go on to the next topic then. So we're actually getting into some dynamics now. So I said last time that we're going to introduce particle kinematics. And this is in non-rotating coordinate systems. In physics 1, you never considered the possibility that a coordinate system could be rotating. You just learned these laws only hold if you have an inertial coordinate system, which means non-rotating and also not accelerating, the origin not accelerating. Well, it turns out we can figure out how to work with rotating coordinate systems, but we're not doing it yet. And I said that there are 4 sort of subsections. The first one is just using the fact that the acceleration vector is defined as the time derivative of the velocity vector, which is defined as the second time derivative of the position vector. Then the second topic is going to be using the chain rule. And I'll just leave it at that for now. Third is going to be relative motion. And fourth is going to be circular and spherical motion. And these two we're going to always use together. They're going to come up together all the time. These are BFFs. Best friend functions. Okay, so the first thing we're going to do is this. And so acceleration is, I'm going to write it with the Leibniz form. Leibniz? I think this is the Leibniz form. d dt of the velocity which is defined as the second time derivative of the position vector. And these relationships are definitions. These always hold. And the first most important thing that you need to remember is don't think acceleration is the derivative of velocity, is the derivative, the second derivative of position. Okay, don't think that. No. Okay, that's lazy thinking. That derivative relationship only holds when you're taking the derivative with respect to time. Okay? If history is any guide, many of you are going to make this mistake. So don't be one of those dummies.
Is there any value to knowing the jerk relationship?
What?
Is there any value?
No, we're not going to talk about that at all. Okay, there's two directions you can go with this. You can go the derivative direction. And that's where you know the acceleration, nope. You know the position, and you want to find the velocity, or you know the velocity and you want to find the acceleration. Okay. When you're going in this direction, it's easy. You don't need any boundary conditions. And all you're doing is taking derivatives. The other direction you can go is the integral direction. So this is where you're starting with the acceleration and trying to find the velocity, and or starting with the velocity and trying to find the position. This one takes more steps. This is where you're using separation of variables. And how many boundary conditions do you need? You need one boundary condition per component. For each integration step. Okay, so what I mean by per component for each integration step is, say that you start with an acceleration vector, okay? And you want to find the position vector, okay? Well, if you're doing it in 2 dimensions, then that's 2 components, okay? And each one of those components, you have 2 integration steps because you're going 2 steps along this line. And so that's 2 components, 2 integration steps each. So you're going to need 4 boundary conditions. Okay. So let's do a couple examples. So the position as a function of time, say, is given as t squared. And we want to know what are the velocity as a function of time and the acceleration as a function of time. Okay, is this the easy way or the hard way? This is the easy way. All we're doing is taking derivatives. If we had to go the other direction, we would, we don't have any boundary conditions, so we wouldn't be able to do it. The velocity as a function of time is just the time derivative of the position. And so that's 1, 2t. And the acceleration as a function of time is d dt of the velocity, which is 0, 2. I didn't tell you what the units are, so we don't know the units, but usually when I use units, it's almost always SI units. So this would be, let's say that all this is in SI units. So time is in seconds, position is in meters, then this velocity would be in meters per second, and this acceleration would just be meters per second squared. Okay, so now going the other direction. Let's say we know that the velocity as a function of time is equal to t squared cosine t. And again, let's say this is in SI units. And let's say we want to know what are the position vector as a function of time and the acceleration vector as a function of time, given that the position vector at time 0 is equal to 0, 50. Okay, one of these is going the easy direction, one is going the harder direction. So which one do we just take the derivative to get?
Acceleration.
Yep. So the acceleration is d dt of the velocity vector. And so that's 2t negative sine t and we're done. But we have to use separation of variables to get the position vector. So we can think of this as dx dt is equal to t squared, and dy dt is equal to cosine t. This first one, the boundary condition that's relevant there, says x at time 0 is equal to 0. And the second one says y at time 0 is equal to 50. Are you with me on how the boundary conditions tell us that? And so now we can do separation of variables. I'm going to start with the x equation. So we have dx is equal to t squared dt. Integrate both sides. So x is equal to t cubed over 3 plus c1. The boundary condition relevant to the x equation says x is equal to 0 when t is equal to 0. So c1 is equal to 0. And now update our function. And we get x as a function of time is equal to t cubed over 3. And now I'll go to the y equation. So dy dt is equal to cosine of t. Separate variables. Integrate both sides. And you get that y is equal to sine of t plus c2. And now this boundary condition for y says when time is equal to 0, y is equal to 50. So 50 is equal to sine of 0 plus c2. Sine of 0 is 0, so c2 is equal to 50. And so now update this function, and you get that y as a function of time is equal to sine of t plus 50. And now if you wanted to put these together in the form of a position vector, you could say the position vector as a function of time is equal to, was it t cubed over 3? Yeah. T cubed over 3 for the x component, sine of t plus 50 for the y component. It didn't come up here because 0 is 0 no matter what angle units you use. But one thing to notice is anytime you're using angles with derivatives or integrals, your angles have to be in radians. Okay. I mean, you can account for that, and so you really could set it up so it's in degrees, but if you're not told explicitly it's in degrees and you're doing integrals or derivatives, you should assume that you're in radians, okay? Because the chain rule would screw everything up if you're in degrees. Okay? All right, so this is pretty much all I have to say about this first one of these four. It's just using separation of variables, taking derivatives, making sure that you're thinking the right direction. It's even now, you know, as I'm practically lying on my deathbed, I have to think twice about like whether I'm going the right direction, acceleration to velocity, velocity to acceleration. So just be careful with, you know, that you're thinking of going in the right direction and taking derivatives when you should and integrals when you should.
Does this class ever deal with derivatives higher than acceleration?
Nope. Nope. Okay, so the next topic is the chain rule. And this is going to be relevant for us whenever, so we're going to need to use this. Whenever we have the velocity vector as a function of a position variable. Okay, so as an example, you know, what if you're given the velocity, but you're given the velocity as a function of x, like say the horizontal location, and that it's equal to x 10x. And you want to calculate the acceleration vector as a function of x. When would this ever come up? Well, it could come up in any conservation of energy problem where you're dealing with conservative forces, and conservation of energy lets you calculate the velocity in terms of the location. You know, like a skateboard going up and down a ramp or whatever. The speed of the skateboard is determined by where you are at the ramp at an instant, right? Okay, so how do we do this? Well, what you don't do is say, this is easy, acceleration is the derivative of velocity, okay? That's what you don't do. Because acceleration is only the derivative of velocity with respect to time. We don't have this explicitly as a function of time. That's the problem, okay? So here's how it works. Let S be your position variable. So that's, I'm just using S to show that this could be any variable defined by an object's position. It could be X, Y, or Z. It could even be combinations of those, but we're only going to use X, Y, and Z. Then the acceleration, remember, is by definition, it's dv dt. It looks like an R. Let me fix that. And I'm going to put this in as a definition. That's never wrong. And the chain rule says dv dt is equal to dv d, whatever that position variable is, times ds dt and now the trick, the reason why this works is that ds dt is a velocity variable. A velocity variable. And we already have an expression for the velocity, so now we can get that from what we know about the velocity. Okay. Okay, so let me show you how this works. So let's say that the velocity is a function of x, and it's equal to x 10x. And we want to calculate the acceleration as a function of x.
Did you just write that down?
Yeah, but I didn't solve it. Now I'm going to solve it. Okay, so the acceleration is dv dx times dx dt. And notice that dx dt is the x component of the velocity. So dv dx is equal to 1 for the x component, 10 for the y component, and now we multiply by dx dt, which is the x component of the velocity. So we're going to multiply now by x, and what we get is x 10x. Okay? You with me on that?
But is dx dt always going to be x?
Dx dt, well, it depends on what your velocity is a function of. So,
I see. So if it's like v of y, for example, be dy dt.
yeah, let me just do that real quick to just show. So let's say that instead we have velocity as a function of z, and this is equal to 5z negative z cosine z. And we want to calculate the acceleration as a function of z. So the acceleration is dv dt. The chain rule says that that's dv dz times dz dt. dz dt is the z component of the velocity. And so this is, so dv dz is 5, negative 1, negative sine z. The z component of the velocity is cosine of z. And so the acceleration as a function of z is 5 times the cosine of z, negative cosine of z, negative sine z, cosine z. Any questions about that one? So the difference between these two was, besides just, taking derivative of a different variable, what the meaning of the d whatever dt was at the end. Okay. In the first case, since it's dx dt, that's the That's the x component of our original velocity. The second one, we're taking a derivative with respect to z, so that's the z component of our original velocity. So the next thing we're going to do, and this is still part of this chain rule discussion, is often let's see, how did I word this? Okay, so often instead of being given the velocity as the function of some position variable, you'll be given the object's path as a function. Okay, like, I mean, you can imagine what that's like if this object is moving along a cosine function, then that's what you would be given for the path. And the object's speed as a function of a position variable. And so this is all the information you need to come up with the velocity as a function of a position variable, and then you can use the approach we have above, okay? So this is enough to find the velocity vector as a function of the position variable. And then you can use chain rule to find the acceleration. Okay, so how do we go from an object's path and its speed to a velocity vector? So picture what's happening here. So say our path is like this, okay? And say that this point here is at the position S, the position variable S. We know the speed. That's that capital V means speed, as opposed to the lowercase v vector. And this is as a function of x. So how are we going to go from this to a velocity vector? Well, what do we want? Like visually, can you picture how we would do this? We would want to get a unit vector that's tangent to this path. And then we just multiply it by this speed, okay? So we want to find a vector that's tangent to this path. Then we want to make that a unit vector in that same direction. Then we want to multiply by the speed. So this is the unit tangent to the path. I'm going to call that u hat. in the direction of motion. Okay, well, how are we going to come up with that unit vector u? That's really the only task we have left. Once we get that, we can multiply it by, our velocity vector is going to be equal to the speed times this unit vector. So all we have to do is find that u. So the first step is we have to parameterize this function. So for example, if we know that this thing is moving along the function y equals x squared, then a parameterization would be x, y as a vector, which is equal to x, and since y is equal to x squared, this. Second, I'm running out of time. We need to, so now that's just a vector that tells you the position of the object at any x value. Now, the derivative of any parameterization like this with respect to the parameter, in this case our parameter is x, is in the direction tangent to the path pointing toward an increasing value of the parameter. Okay, so for example, in this case, I'm going to call this vector u with a vector over the top. It's not a unit vector yet. But this is equal to, if we take the derivative of that vector with respect to x, 1, 2x. In this case, the direction that I've drawn this arrow is toward an increasing parameter value. It's toward an increasing x value. So we don't have to mess with the sign of this. If I drew that arrow the other way, we'd have to multiply this by -1. I'll do more examples of that. And then last, so now how do you get u hat? That's just equal to 1 over the square root of 1 plus 4x squared square root times 1, 2x. All I did was take the unit vector in that direction. So I haven't solved for the acceleration yet, but, well, let me just finish this thought. So number 4 says, okay, now the velocity is equal to the speed, whatever that is, times that unit vector that we know now. Okay, I'm going to stop there, and we'll do some examples next time. The math gets messy on these because now you have to take the derivative of this. It's pretty hard to come up with examples that don't get messy, but now we're at the point where we can use the chain rule to calculate the acceleration. Okay, have a good weekend. Unless you're in D form, don't have a good weekend yet. We have one more hour of bad weekend.
D-form is actually fun though.
Yeah, D form is awesome.
This is